It's a pleasure for me to chair now one of the two dual plenary sessions. So the topic of our session is the future of the electricity markets. We already have heard that there are many challenges ahead of us. On the one hand, we have rapidly increasing renewable shares. On the other hand, we also have heard already this morning that we have an increasingly electrification of the energy systems and therefore the electricity markets and how we design our electricity markets is very crucial and important. And in our session, so we have three presentations. And I think it's these presentations, they are excellent contributions. On the one hand, looking to the very long term, so how we can maintain resource adequacy in our system. On the other hand, we also discuss short-term aspects, how we can implement flexibility in the systems, and we also have a contribution where we have an implementation, a real-life case, how sector coupling, flexibility provision can work in practice. So the three presenters are on the one hand Richard Green from Imperial College Business School, Reinhard Haas from Vienna University of Technology, and Markus Krewig from Windnode in Germany from this consortium. And it's a pleasure for me to introduce our first speaker, Richard Green from Imperial College. And he will talk about contracts for renewable and conventional electricity generators. Richard, the floor is yours.
Okay, thanks. Okay, well, thank you very much. Also, thank you to the people shutting the doors for stopping those who aren't good at timing from polluting the room. So it's a pleasure to be here. And if you looked at the program when it first came onto the web, I hope nobody booked in the expectation I was going to talk about sort of the future of EU market design and regulation. Firstly, it would have been a little bit ironic to have somebody from Europe's silliest country speaking on that particular topic. Secondly, anybody thinking that they could add anything to what Alberto was going to say and now has said, that would be an odd decision. So instead, I'm thinking about market design, perhaps slightly more abstract, but definitely guided by the sorts of challenges that Europe is going to have, and thinking a little bit about various trends going on and how we need to respond to that. And sometimes you see a line that slopes down, and it's a good thing. Renewables are getting much cheaper, and cheaper than some estimates of the cost of power from fossil energy. And sometimes you get a line that slopes down, and it's not such a good thing. For instance, if you held shares in some of Europe's incumbent electricity companies. I don't think they're on the list of sponsors, these ones. And these things may be connected, of course. If you're not too good at econometrics, you'd be looking for the correlation between X and Y, whereas in fact it's probably Z affects both X and Y, with Z being the general increase in renewable capacity, driving down renewable costs, and driving down or driving up the competition to the incumbents and therefore down the share prices. And we can see that with what used to be the neat, from the standards of I-econometrics, which I tend to prefer to econometrics, sometimes the good relationship between gas and electricity prices in Germany, which was nice when it lasted. And the reason for the divergence is somebody or somebodies added rather a lot of renewable kit and drove down the prices. And so this is not a market that is working particularly well for the incumbents at the moment. It may be something is working quite well for the renewable generators, but that's probably not I'm not sure we describe it as a market at this moment. So that's perhaps a problem. Is it a problem in theory? Well, in theory, we have got the short-run merit order effect of the residual demand that Alberto mentioned in his slides a while back, gets depressed by the presence of lots of renewables, so prices come down, and conventional generating companies are unhappy with low prices. And if you're a company and you're unhappy enough for long enough, then you start thinking about exiting the market, and as you do so, then the prices would come back up again until some of you, those of you who stuck it out the longest, were happy again. And indeed, so we have a low duration curve, and you don't change the peak generation very much because you might have times of high demand and little renewables, but there will also be times of low demand and high renewables, so some very low outputs. What that does to the overall pattern, of course, is that you need a lot less base load and a bit more peaking, and the overall impact on mid-merit plant is ambiguous depending on the shapes of your lines. But somebody doesn't like ambiguity, which is fine. I don't mind unintelligible heckles. So I say, please do stay if you want to, from my point of view. So in theory, this is a market that is working. But what sort of signals do we get in practice? Well, this is Jim Bushnell and Kevin Novan have a nice paper looking at what solar power is doing in California, and Jim kindly shared some of the data so I could do my own version of his diagrams. And you get the load. In 2012, there was very little solar, and you had a pattern of prices. If you skip forward 4 years, you have a rather more solar power, and you have, therefore, exactly the sort of steep ramp for everybody else that Alberto was talking about with his 99.9th percentile graphs. And you have nice low prices when the solar is generating, and you have slightly higher prices when everyone else is scrambling to make up for the fact that the sun has just gone down. And all in all, that's not necessarily good news for the renewables. And this is British data showing the average price received by solar dropping rapidly relative to the time-weighted average. Nuclear runs all the time and gets to time-weighted. Fossil, increasingly concentrated into the times of higher residual demand, gets more. And wind has the same impact on its own market as solar, but Britain is windier in the winter when prices are higher, so it's not quite as badly affected. But even though the price of fossil is going up, is it going up by enough, given that plants that run for less time will have higher average costs? And even though the costs of renewables are going down, are the costs going down fast enough to cover the lower prices? Thomas Olivier Loutier and I think of this about a race between prices and costs. Who's going to win? And if the prices win the race, that's not good news for the future of unsubsidized renewables. And if you think, and this is all sort of static and perhaps a market in disequilibrium, what about the long term, if the long term is ever equilibrium, which it probably isn't? But if this takes a simulation on 17 years of weather data and demand data with quite a lot of renewables, and the year-to-year variation, renewables have a coefficient of variation, standard deviation over mean, sort of 6% for wind, 2% for solar at the level of a fleet. slightly worse for individual stations, I'm sure. Baseload plant does have a little bit of variation in how much it can produce, mid-merit a lot more, and the peaking plant have a huge variation in what they produce, and I decided not to try and put it all on the same scale. If I think about the return on capital, or the return to capital, the money available after fuel costs, after variable operations and maintenance cost, again, you have quite a lot of variety in how much you have available year to year. Would that worry your bank manager? It would probably worry your bank manager if you had too much debt. And of course, having a high proportion of debt is one of the ways to reduce the cost of capital. And for these guys, which are very intensive, capital-intensive generators, having quite a high proportion of debt is probably quite good news in terms of keeping the overall cost down. And therefore, these risks, although I haven't yet tried to match these simulations with anybody's balance sheet and financing plans to see how much debt they could sensibly carry, these simulations may look like bad news for the cost of capital if you rely on the market alone. And where did my title come from? I was reading a couple of papers put out by other UK-based researchers thinking about what could we do if the large presence of renewable generation and variable renewables might be sort of contaminating the market not only for themselves but also for everybody else. One answer is separate them, stop them from contaminating. Michael Liebreich has spoken about have multiple power markets and have them clearly separate, clearly defined and separate for the variables and the dispatchable power. Malcolm Key and David Robinson have suggested there should be separate markets not only at the wholesale level but also at the retail level, so consumers should decide how much as available power they to buy and how much dependable power they should buy. I have to say, given that there's a lot of evidence that the average current consumer has difficulty differentiating between the average price they pay and the marginal rate per kilowatt hour, I'm not so optimistic about that particular aspect of the proposal. And also, two markets that need to be coordinated. I don't know how many people in the room remember the twin pool approach. It flourished very briefly in the summer of 1989 when England and Wales were working out how to privatise our electricity industry. We would have one set of contracts owned by generators. We would have one held by generators. We would have one set of contracts held by retailers. And they would have complex swapping amongst themselves to work out which set of contracts should actually be called into operation. It lasted about 6 weeks before everybody realised that two separate markets were not likely to work particularly well. I think at that particular time it was the advent of the competition lawyers that was causing the major problems. But nonetheless, not good news. And really, once we get to delivery, we don't have two types of electricity. We have electrons moving through the system. And so delivery, I think, one market. But that doesn't necessarily mean we don't want two types of contract. Because here is a set of variable generators, a not entirely random week of British data. I wanted to choose a week that was going to show what I wanted. Because here's another set of generators during the same week, and the question is, which are the variable, so-called variable renewables, and which are the non-variable or dependable fossil? Is it obvious? Well, I've actually slightly misled you which is which. So I'd forgotten how many inserts I had. I actually slightly misled you the way I put my first title around. But basically, the fossil are going up and down almost as much as the renewable, although, of course, the difference is the renewables their generation is led by their availability, whereas the fossils and their output is led by their demand. So that there are two types of operation, maybe that implies we want two types of contracts. So for the demand-led generators, they've got a mix of capital and variable costs, and we don't know when they're going to run, but they run when somebody wants them. That feels like a call option. I have the right to make you sell to me at a fixed price, and I pay you something in return for that. The fixed payment covers my capital costs, and the exercise price for actual generation covers my variable costs. Not very risky for the generator, helps keep the cost of capital down. If you have a pool-type market, it's a one-way contract for differences. For the availability-led generators, well, they want to be able to sell at particular times. Their capital costs are dominating. So a standard put option is what you would have if I want to be able to sell a particular price when I want to. But of course, the slight issue with those is that if I had an availability fee based on my fixed costs and an exercise price based on my variable costs, which minimizes my risk because then I don't really need to worry about quite how much I produce each year, that's not going to be brilliant news when you think about normally you have a put option that you exercise when the price in the market is low, so you can sell at a higher price. And I'm suggesting that what actually you want is that you're selling at a low variable price, even though the bulk of the revenue is going to come from times when it's high. Maybe you could have you could call it an exclusive put option. In other words, I can tell you when I'm going to sell to you, when it's windy or sunny, and I'm not allowed to sell in any other way. And if the terms are right, if the fixed fee is big enough, I might be willing to accept that, even though I'm actually selling power at a low variable rate when the price in the market outside is quite high, but it might be worth my while for a big enough fixed fee. And I guess you could write a similar availability CFD where you get payments or you make payments in return for an upfront fee only when your plant is available. If you had anything that said, I will pay you something every hour of the year, that's going to be seriously bad news, because the times that you may not be able to generate are the times when the price is going to be high and you are now contracted to pay a lot of money back. So it has to somehow be linked to your own availability if it's to get these risks down. There may be a bit of fun for the lawyers in writing that contract. I believe the British National Grid Company is now actually monitoring and measuring what the potential generation at each wind farm is for the big farms, and therefore that could go in to be a contractable variable and hence part of a legally watertight document. But this isn't the International Association for Energy Law, so I'll move on. In a sense, feed-in tariffs are a kind of put option without any optionality, in that you have to do, if you've got one, that's what you're going to get, whatever the price outside is. And in the past, it's had effectively a very high exercise price, usually above the market rate, and therefore that's been good. And the seller of the power, however, takes the output risk. Two-part output contract of the sort I'm talking about would try to replicate this sort of feed-in tariff, and you get a fixed fee for the cost. Who would hold these contracts? One possibility, the retailer buys power firstly from the availability-led generators, but also from the demand-led generators, as in the fossil. So the availability have this sort of output contract or availability CFD, demand-led more a conventional call option. The availability risk would be split between the retailer and the wind generator or the solar generator, if the exercise price in the contract is quite low, then the payment from the retailer is basically going to be fixed, not very risky for the wind generator. But then if it's not a windy year, and really for financial risk, we're thinking about a year, not a day. If your bank manager is worried about your daily results, you're in trouble. If at the level of a year, if it's not a windy year and the retailer has to buy a lot of gas power generation, that's bad news if they've paid a fixed fee to the wind generator. On the other hand, if there's a lower fixed fee and a much higher rate per unit for the wind generator, then if it's not windy, the wind generator gets less revenue, the retailer has more money left over to buy gas-fired generation, it's less risky for the retailer. So that's a balance of where do you wish to put those risks, whose balance sheet is in the best situation, what's it going to do to the cost of capital. It could be that the availability-led generator is actually, in a sense, the lead contractor and buys back up from the demand-led generator. They then carry the availability-led generator. The wind generator then carries their own availability risk. It might actually be equivalent in some way to a proposal by Dieter Helm in a review he did for the government that said you should have equivalent firm capacity auctions, although he was concentrating on capacity rather than energy. Or it might be that the demand-led generator's in the lead and buys cheap wind when it's available. That gives, again, little risk to the retailer, and the availability risk depends on the price in the contract between the wind generator and the gas generator. What sort of risks do we get? Well, these are, again, the rents, the money available to pay back your capital, looking at the coefficient of variation. If there's no contracting, generator costs from year to year vary a bit because the availability risk of wind and solar will affect how much we're running our fossil plant. The market value varies much more. The years when we've got a lot of gas generation are the years we have a lot of high prices, we have higher prices. And the generators' rents vary even more, also for the availability-led generators. If we have the sorts of contracts I've suggested with the retailer in the lead, then the retailer's costs come down, the generator's risks come down. It feels like a safer option. I could change the strike price for the wind generators, and I reduce a higher rate, the retailer's cost goes down, and the availability-led generator, the wind generator risks goes up. Again, simulations and talking to financiers would expect which of those might be better. How are you going to run that? I think you could have forward sales fixing the volume, or say FDs with a pool. The marginal sales are always going to be at the spot price. If you have options, again, you buy up to a quantity. If you need any more, you're still facing the spot price, so you're tending to get the right marginal signals. My view is that having a pool-type market and contracts for difference means that sort of sensible choices get made automatically and don't give people too many chances to make mistakes. David Cameron. How many markets should we have? Well, economists do tend to spend a lot of their time looking at the energy market in a sense before real time happens. And I guess if I'd said I'm going to talk about two markets in the 90s, I'd have been talking about energy, spot market and contract market. In the noughties, maybe energy market, capacity market. But actually nowadays, we need to think about balancing energy in real time, the reserve that gives you the ability to provide balancing energy in real time. And nowadays, with a lot of plant that doesn't have inertia, isn't spinning round directly connected to the grid, wind turbines are only indirectly connected. If something goes wrong, it goes wrong faster than it used to. Maybe you've got some fast response and batteries, or maybe you've got a problem. So we need to be thinking about those, and perhaps on a slightly controversial note for this association, don't only study the energy side, look at the ancillary services as well. Thank you.
Okay, so for your presentation, so if there is one short question, we could address it, but I recommend rather to have a panel discussion after the three presentations. So in case not, I'd like to introduce my colleague Reinhard Haas from Vienna University of Technology, and Reinhard also will talk about the challenges we are facing at present in the electricity markets, and he'll also address shorter-term operational aspects. So Reinhard, the floor is yours.
Hvala Hans, dobro jutro, good morning. It's really a great pleasure to be here at this European conference in this prominent circle and to discuss with you some of our reflections regarding the democratic and sustainable possibilities in electricity markets. In my presentation, I will shortly present the motivation. I will explain our method of approach, discuss how the variable renewables impact the market, explain the core problem of capacity payments and the role of flexibility, how much peak should we store, and finally we will analyze the subsidization of renewables, and conclusions will complete my presentation. So for the introduction, motivation, we have had some introduction by Alberto on the clean energy package, and one of the major focuses, pillars of the energy package are the energy communities. Second, it is not possible to squeeze, to force variable renewables into the system. We have to provide proper financial incentives. And third, there is currently a strong, and I would say an increasing desires of at least some electricity customers to participate in their electricity supply. With respect to the development of energy carriers for electricity generation in the EU 28, we have the following picture up from 1990 to 2018. And what is the most interesting, most squeezing perception of this figure is that from about 2013, the renewables are no more alternative energy carriers, but they are, let's say, the mainstream, generating more than coal and generating more than nuclear power. Coming shortly back to the clean energy package, in the structure of this package we have focuses on energy efficiency, renewables, interconnection, and so on. But one of the major pillars is the electricity market design, and what Richard just told us is also going into this direction. Our core objective is to identify major boundary conditions to integrate even larger amounts of variable renewables into the electricity system. And in this context, it is very important, and I discussed shortly before with my colleagues speaking here, we will not discuss policies in our countries, but we try to provide basic principles that are applicable, let's say, almost universally. And my reflections are based on electricity economic point of view, so one may add that from the supply securities point of view, there should be some additional features. These are not discussed in my presentation. Our method of approach is based on hourly resolution of residual load. We do scenarios with large quantities of variable renewables, and we apply in principle fundamental models to calculate electricity prices, electricity spot market prices, and we integrate flexibility measures, storage, and also elasticities of demand in a dynamic framework. Just to repeat the basics, as already also shown by Richard, here we have a merit order curve, and intersection with demand gives the price equal to system marginal costs. If at a certain hour we introduce now a specific quantity of photovoltaic, the curve will be shifted to the right, and we have an intersection at a price which is much lower. And if we look at such a development over a week, here we have the violet curve which shows demand, and at some points of time we have more electricity from variable renewables, at others we have less. So we finally obtain a so-called residual load curve. And I would say base load is an anachronistic term in this context. So the residual load shows the actual load minus non-flexible generation. And we see we have excess electricity at some points of time and under coverage at others. This finally leads to a pattern of short-term marginal cost pricing. And here we see that we have maybe at a price shown here with the broken line, average price, and at some points of time we have much higher prices, at other points of time we have much lower prices. So even if we have low average prices, we might have a, let's say, a significant price spread, and such a price spread provides incentives for maybe storage or other new flexible solutions. An important issue, important component in the overall market price, the ahead price, is the CO2 price. And while we had low CO2 prices of about €5 per ton CO2 over a long period of time, until the end of 2017, since about mid of 2018, we have rather high, new high prices, and this is mainly due to different changes in how this CO2 market is organized, and that some parts of the certificates are taken out of the market. But this, let's say, rather high price has on the other side also influenced the day-ahead prices. Richard has also shown some part of this figure. This figure goes until the year 2016. And already about 2011, we had something like convergence in this market. And what is important is that from about 2012 to 2016, we can see a steep decrease, almost a nosedive of the electricity prices until 2016. Now let's extend this figure until 2018, and we can see that we have a quite different picture after 2016. That is to say, the prices went from 30 to about €50 per megawatt hour. And at least to some extent, we will attribute these increases to the increasing CO2 prices. I have shown before the residual load over a week. Now let's look at it over a year and classify it. That is to say, red is 2016, blue is 2030, and we have under coverage here above the black line, and we have surplus due to excess generation here at the right side on the bottom. And we can see 2030 we have much more surplus due to excess generation. Now this classified residual load curve shows on the left side on the top this, let's say, high peak load. And the question finally is, how can we cover this part of the curve? In Germany, they call it kalte Dunkelflaute, so an English translation could be called dark lull, where we have no wind and no solar. And finally, there are two extreme positions. Hans has already mentioned it with system adequacy, so by a regulated capacity payment or by competition between supply side and demand side technologies and behavior. So in the second position, we try to use all possible technologies and other options to finally meet this peak load. Let's first look at the issue of capacity payment. So all regulatory capacity payments for power plants, matter of fact, distort the energy-only market and lead to wrong price signals for all other options. And price peaks at times of scarce resource should actually revive the markets and lead to effective competition. In addition, the higher the conventional excess capacities are, the lower will be the share of RES. So the target is to strive to retain system resource adequacy by means of correct price signals. The other option to cover this area is flexible coverage of residual load. And the first important measure in this context is the extension of the transmission grid. So I would say a well-functioning, broad, large transmission grid is a major precondition for using flexibility measures, and it is in itself also a flexibility measure. The second issue is that we will have rather high prices at this point of time. In Germany, they discuss about even 2,000 euro per megawatt hour in some of the German journals, and this will also lead to some reduction in this context. Finally, next we have load reduction due to demand side management in a technical way. We know cycling since I think more than 50 years for heating and night stove heating. And then we have here the flexible power plants. So in the discussion between the, let's say, apologists of the capacity markets and those of flexibility, we have to bear in mind that even if we focus on the flexibility measures, we know that we will use some flexible power plants, like, for example, combined cycle gas turbines. Only afterwards we may use storage, but the problem of storage usually is they are empty when they are really needed. So what we can here identify is the capacity which we need without insured payments. And we can now compare the case of capacity with insured payments and without, and we see that in the later case with insured payments, we just have much higher capacities. The next issue is what do we do at times when we have a large quantity of excess capacities. With respect to this, let's say classified residual load curve, we have to look at the corner on the bottom on the right, and we can see that we will have high excess capacity at very few hours. So the problem of storage is that the storage economics, effectiveness of cost effectiveness decreases with additional storage. In this figure you can see, first we try to store the yellow area. So the yellow area will be stored, and we will have here in storage 1 full load hours in this magnitude. If we add a storage to store the green area in storage 2, we will see that the full load hour of storage 2 are much lower. And this leads to the problem of all storage. The more storage you build, the less attractive are they from an economic point of view. And also in this context, for coping with the excess electricity, the extension of transmission grid is one important measure. Next is we can also use shedding, for example, of wind power plants to reduce this peak load to be saved. And we can add direct marketing because the prices here will be rather low. Again, we might have some technical demands at management. Smart grids will not contribute by quantity but by quality, because we can shift from one voltage level to another, for example, photovoltaic electricity. And then at the top of this, we might also have storage, but only if the storage has reasonable full load hours. One of the most pressing and mostly discussed issues is how long should we subsidize the renewables? And Richard has already presented in his first or second slide the impressive learning effects we had for photovoltaics. And I have another figure which similar effects. We can see here over the time from 2004, we have a decrease in the costs of photovoltaics, which is the blue curve, and we had the green curve, which shows the household electricity prices. There's something that is called grid parity, which means the costs are equal to the household electricity prices. And of course, we cannot use all electricity generated in this context here, but we have an increasing, let's say, gap which contributes to more and more cost effectiveness of the decentralized PV system. Finally, one discussed issue is digitalization. We also have heard the word already today. And another one is that we can have something like blockchain, or that we can have peer-to-peer trade beyond the meter. And the idea is, for example, here we have a multi-family dwelling, and we have the meters of different customers in this multi-family dwelling. We can put a photovoltaic system on the roof, and there is something like a tenant electricity model where PV electricity from the roof can be contracted to the customers. And we can have a certain amount contracted to customer 1, another to customer 2. But behind this meter, the customers may trade their electricity from the PV system, for example, via blockchain or a similar application. And this is done more or less without involving the supplier or the balancing group, or as Richard has called it, the retailer. So this model is something that is optional for the future and could also contribute to decentralized and more democratic systems. There will be, I think, a specific dual plenary session tomorrow where the major focus is on these decentralized issues. So what I think is important, that we enter now an age of new thinking, which makes the electricity system more democratic. And we have the generators on the beginning of the chain. They feed electricity into the grid. We have a centralized storage, more or less the same as we had it the last 50 to 100 years. But further, we have the supplier or retailer, And at the end, we have the prosumator, a term I think created by Richard. And the prosumator means this is not just the consumer and not just the prosumer, but the prosumer producer owns generation units, but owns also some storage. So in this future system, we have a bidirectional way of flowing electricity, and we have a broad, comprehensive range of flexibility options. My conclusions are, if we want to head towards a sustainable electricity system, it is important to integrate a broad portfolio of technologies and of demand-side options. There is no single technology which will solve all problems. There is no quick fix, there is no one-size-fits-all solutions. And I think it's important to recognize that larger market areas are favorable. It is also very important to have correct price signals, including also the CO2 price signals, despite I know that the word correct price is very difficult to put it into practice. So we should be satisfied correct as possible. Most urgent is to exhaust the full creativity for flexibility of all market participants, as Georg Erdmann has already written it, I think 6 or 7 years ago. Regarding the capacity payments, we have simply to bear in mind that any capacity payment will distort the system towards more conventional and less renewable capacity. Regarding the prospects for storage, I think we should be a little bit more cautious. If we look at it from an energy economic point of view, the prospects are less bright than argued usually by technicians who just want to balance the energy. And I think it is important to recognize that the new key players will be the suppliers, the retailers, the balancing group, and no more some single large generators. Thank you for your attention.
Okay, presentation. You have given us some hints how we could manage flexibility provision. So from a system analysis point of view. And now I'd like to hand over to Markus Grevig. So he will talk about flexibility provision and also sector coupling of a pilot project and implementation in Germany. So Markus, we are looking forward to hear more about your wind node project in Germany. Thank you.
Yeah, thank you for the kind introduction. Dear colleagues and dear babies, I don't know if our youngest participant is still there. If not, I invite them to return, because it's basically it's their future we're talking about here. So very warm welcome to be back in the room. I'm going to present to you some first-hand experience from a project we're running in East Germany about basically all these flexibility and renewable market integration issues we have been addressing this morning. So it's maybe a little less theoretically founded, but I'm going to try and talk about a few findings and a little bit of experience also from a methodology side of running such a project. WindNode, which I'm going to introduce to you in a minute, is currently the biggest consortium project in East Germany dealing with system integration matters of renewable energy. So what I'm going to try and tell you in that short amount of time, I would like to start with a few comments about the German case of energy transition and share 3 observations with you. Then secondly, I'm going to introduce the WindNode project, what that actually is and what we're doing and what we found so far. And finally conclude with a few ideas about regulatory sandboxes. Well, oh, sorry, I think that was the laser. I'm not going to do that again. So the first observation, and you don't need to read all the details on that slide. It's a wonderful analysis done by Georg Erdmann, who's mentioned twice now, about the status quo of German energy transition. And in a nutshell, the energy transition so far has been an electricity transition. So everything about the electricity transition, the share of renewables in the generation mix, and even the stability of supply measured as SAIDI, and the phase out of nuclear power is all going very well. And all the rest of energy transition is lagging behind. Most importantly, our CO2 reduction targets, but also aspects such as mobility. So that is the short message here. And the implication is we need to think about sector coupling. The second observation, I like that slide, it's the composition of the German electricity mix over the last 20 years. We have now arrived at something like 40% the first half of this year. And it's volatile sources. So unlike other countries, this is basically wind and solar with all the challenges it brings. What we've done after a series of phases in and phases out of nuclear power is basically a substitution of nuclear with renewables. We haven't touched especially the lignite part so far, and that is part of the very current discussion about a coal phase out, which has now been decided to happen within the next 19 years or so. Yeah, I'm gonna get back to that nuclear issue in a second. And the third observation, and that might surprise you a little bit because that's not really energy economics, is a question about how we talk about energy transition. I doubt that any one of you knows that publication. It came out in the late 80s. I found that in my mother's library, who subscribed to that publication in the late 80s. And it basically says, radioactive food, the avoidable risk. So people subscribe to that publication to know which food would glow in the dark and which one you could feed to your kids. And I think it's very important to understand at least the German soul of energy transition, to understand that fear of nuclear power. And my hypothesis is that the story of talking about energy transition has been a story and a narrative of fear. It was the fear of nuclear first, then 20 years after, that fear has gone down a little bit, and the fear of climate change came up. Then Fukushima reminded people that there is still a risk of nuclear power, and then at least Germans were afraid of both. And I don't mean to make that ridiculous in any way. I feel personally committed to avoid both of these risks. But my point is, I think we need to reconsider the way we're talking about energy transition. Is it only a story of threats, or is it also a story of opportunities? And I'll get back to that later. I'm not going to talk about the economic part. You all know that much better than myself. So these issues are basically, they set the stage for an initiative launched by the German Ministry for Economic Affairs and Energy about 4 years ago. So they wanted to start large-scale showcases, Reallabore, like living labs, and the target was to find scalable solutions for efficient, eco-friendly, and safe integration of large amounts of renewables, basically addressing more or less these issues I was talking about earlier. So it's coping with intermittency once we're going into even higher shares of renewables, of volatile renewables. It's secondly the question of how can we decarbonize other sectors, how do we utilize digital technology, and I personally added the fourth point because I believe that whole social aspect is still needs much more emphasis, is the question of how do we develop more attractive energy transition narratives. The government's spending about €250 million over 4 years. We have now finished the first 2.5 years, and the project project will run until 2020. Altogether, 5 big consortia all over Germany, which represent different situations of a grid structure and generation structure. Broadly speaking, the southern part of Germany is the PV part, which challenges the distribution grid and the lower voltage levels much more. And the northern part is the wind part. East Germany, which is the dark green part, and at the same time is the area of our project, is basically a wind-dominated region where only there are basically load centers in Berlin, the capital, and further south, and not very many people are in the north. So it also brings the whole issue of grid extension and so on and so forth. So WindNode, as the biggest and obviously the most beautiful of these 5 consortia, contains of 6 federal states, about 16 million people, 1 control area with a slight exception of Hamburg, which is 50 hertz, the TSO 50 hertz, and has already close to 60% of renewables in that regional mix. So that's like the setting for our project. More than 70 partners, and by the way, you don't need to learn them by heart right now. I have some flyers here if you're more interested, so please feel free to pick one up or check out our website. That's just to show you the idea of this living lab is to really create a real-life ecosystem of a whole network of players involved in a real energy system setting and transition. These 70 partners are working on 50 individual projects under the framework of WindNode. No worries, I won't talk about all of them. I just tried to group these activities in 4 key areas of action. These are only 3 here, so the 4th one is still coming. The story is about utilizing flexibility to cope with intermittency. No need to study that picture. That has actually been drawn for a lay audience. The idea of flexibility starts at the first field of action by identifying flexibility options without even asking for any business model. So it's about it's about the technical potential of flexibility. And first of all, that is demand-side management or shifting load, by the way, not on a consumer level. So we're not talking about washing machines or such, but we're talking about commercial and industrial users. For example, Siemens in Berlin, with 4 of their factories, they expected to find a flexibility potential of 4 gigawatt, ended up finding more than 20 gigawatt. A big success story, because also the initial resistance to that project, if you imagine someone in charge for that factory, they won't applaud in the beginning that there's another energy project coming, but there were some very nice side effects of that search for flexibility. For example, they found one problem for voltage stability, which caused quite substantial losses. As a side effect, could fix that immediate gains, even though that doesn't have anything to do with flexibility itself. But the story shows that once you start looking for flexibility, that worked very well. Sewage treatment at the Berlin water utilities, Lidl and Kaufland, one of the biggest supermarket chains, there are 1,000 of their supermarkets in that region, and obviously if you aggregate them and use all that refrigeration, there's quite some nice potential for load shifting. And a few others, plus the idea of sector coupling. Sector coupling involved in this project is power to heat and power to cold, no power to gas. Power to heat projects are quite impressive. One of the biggest ones in Europe, 120 megawatt at Vattenfall. What we don't have is power to gas. And the reason that we don't have power to gas is that when we started that project 4 years ago, the general belief was still that power to gas is so far away from the market that even with all that public funding, there will be no one investing in any kind of substantial power to gas facility. I believe that that feeling has changed over the last year or so. Okay, so just a few examples. Now, the exciting second step is about the business models. And one of the focus of this project is on market-based grid congestion management. So we're not attempting to substitute the entire regulated redispatch process by any kind of a market-driven process. But the idea is to collect a certain group of flexibility options which haven't had a chance to contribute to grid congestion management so far. So specifically the group below 10 megawatts. Therefore, and the whole thing can be summarized under that idea of smart markets, if you will. Therefore, 50 Hertz as the TSO together with the involved DSOs have built up a flexibility platform. By the way, that includes quite some nice exercise in TSO-DSO collaboration, which we have heard about earlier today, and that alone is a great gain from that project. Seems to be marginal, but that process of TSO-DSO collaboration is an important element here. That platform has gone online a few months ago. First trades have been done, and that is one example of these real-life projects which are now being tried out. A very interesting side remark. Imagine you're talking to someone like Siemens or Lidl or you name them and ask them to participate in such a project. Now, the idea is we make better use of flexibility, we use that for grid congestion management. Sounds all very good and reasonable. Now, the problem is there is some prohibitive regulation, at least in Germany. And the way it goes is there is strong regulatory incentive to maintain a very flat load profile over the year. So if you do that, you gain much cheaper grid fees over the entire year. And if you violate that very flat load profile for only 15 minutes, because you're using let's say there's some strong wind generation and Lidl or Siemens or whoever uses up that power peak, so they violate their very flat load profile, they will pay substantially higher grid fees. That is obviously an anachronistic element of regulation, but it's still there. And that seemed to be prohibitive for even running such an R&D project. So we talked to the ministry and negotiated something which is now called regulatory sandbox. So it's a regulatory exception which allows participants in that program to run these kinds of experiments without suffering any disadvantages compared to the kind of grid fees and some other elements they were seeing before. So that is really regulation on a federal level. It's a federal law behind that, and I believe that is quite unique so far. And I'm pointing that out because I believe the idea of regulatory sandbox has proven to be very powerful. So we need to integrate the regulatory framework in our thinking and our experiments, and we have seen that a large number of partners started joining the project even without any public funding, but only having that perspective of being allowed to try that. In the end, it didn't work out perfectly. One of the reasons that that regulatory sandbox ended up being a little bit disappointing is its limited lifetime. So it only runs for these 4 years of the project duration. Now, imagine someone investing in something in a 20-year lifetime asset or so. 4 years is simply too short to make that investment decision. But I believe that that problem could be fixed, and therefore I do believe that regulatory sandboxes are a very powerful element for energy system innovation and also regulatory learning. Okay, so maybe one more aspect about the flexibility platform. I can't promise to you that this will in the end turn out to be a solution which will be rolled out and implemented. Let's see, I don't know yet. But one of the discussions and also academic discussions going on right now is the question of whether or not something like this flexibility platform for grid congestion management can be viable in a context of a zonal price system, or if there will be some kind of strategic bidding like increase, decrease gaming. So the idea of someone who has sufficient market knowledge and sufficient size can manipulate the market and somewhat create a congestion situation which then they will fix again and simply earn that money. Okay, so third aspect, which I will skip due to the limited time, is different aspects of digitalization. Maybe Andreas, you want to raise your hand because Andreas from Technical University Berlin is the one in charge for digital aspects of the project. So if anyone is interested, please approach Andreas. And I want to talk about another element that might be surprising to you, and that's some experiments about new narratives for energy transition. And don't get me wrong, this is a very minor part. We're talking about around about 1% of the entire project, but I still feel it's worth mentioning because we are running experiments together with artists, together with literature science, and others more to try and find ways to better connect to people in the way we talk about energy issues. And one of these nice little experiments, which people found ridiculous in the beginning, and then everyone wanted to participate and loved it, so all the CEOs and professors involved, is what we call energy and art. So we set up 50 working groups of energy professionals together with artists, and the question was to create a picture together. And all these 50 pictures are in this little book, so if anyone is interested, please feel free to have a look at it, and first come, first served, you may also take that home. But the learning is that this created a whole new dynamic in thinking about future energy solutions and gave the whole thing a much more opportunity-oriented spin. That's why I'm mentioning that aspect. Okay, I'm trying to wrap up. 2 minutes, yeah, should be feasible. First remark is about public R&D projects. At least the German way of thinking about public R&D support for the energy transition. Besides the established pillars of basic research and applied R&D, the government is currently introducing a third pillar, which they call showcases or living labs or Reallabor in German. The very systematic definition is by TRL, so technology readiness level, and they just call everything above TRL 6 a showcase or living lab. From our experience, we believe that living labs or showcases are more than only close to market, and have at least 3 interesting aspects. The first one is high visibility for a comprehensive ecosystem approach. That's what I try to point out. The second one is the regulatory sandbox approach, which I already talked about and which I believe in a modified form will be a powerful instrument, maybe even more important than only public funding for energy research. And the third one is a new way of developing energy narratives, which hopefully not only let us talk about nuclear challenges, but also opportunities for innovation and others more. And finally, that's my final slide. I brought you one example, again from Germany, in which I believe that sandbox approach could be applied. That is the phase out of lignite over the next 19 years. There are basically 3 lignite mining regions in the country. which I highlighted in that map, and they will receive about 40 billion euros public support over 2 decades for phasing out lignite. That's a lot of money. And if you put that in relation to the jobs affected, that is round about 1 million euros per job. So quite a lot of money. And still, there is a feeling that the amount of good ideas and structures in that region is lagging behind the amount of money which is being spent. So first of all, it's an invitation to anyone creative and also other transformation regions. So I believe this is a process where there is a great opportunity for transition regions in Europe to unite and develop best practice ideas. But I believe this is also a potential application for something like this regulatory sandbox, because first thing that happens when you announce these big numbers is opportunism. People have these euro signs in their eyes and think about everything they always wanted to buy. And besides that, you need to put out long-term incentives which point into a desirable systematic future. We all know that it's time-consuming to develop regulation, and that bridging element between regulation as of now and the desirable future of regulation, I believe, is regulatory sandboxes, because they are quick and they offer the chance for regulatory learning. Thank you.